Hey everybody, welcome back to episode 3 of making a NES emulator from scratch in Python 3. My name is Andy, and yeah, we're just going to keep going today. We've been doing what we've been doing, which is implementing some instructions and trying to get this CPU to work. So yeah, thanks for tuning in or watching on YouTube or whatever you're doing. And let's get going. So just a bit of a check up on what we did last time. So we kind of ended up last time having implemented a basic structure for the RAM, the PPU, and the CPU. They don't really do anything at the moment, but getting some memory in there, as well as some things that can more generically control memory and be able to set and read from memory locations. The goal for today is going to be to do some more instructions primarily. And to do instructions, we're going to need to be looking at our indexing modes, so our addressing modes, so how we can read the instruction from each operation that's going to be coming through our CPU, and how we can turn that into a correct memory address and then do something with that memory address, so store it on a register or whatever. I'm just going to start off by doing a few things that kind of left me a bit perplexed last time and I wasn't quite sure how to fix. I figured out how to do them. So it turns out that the first one was that this is expecting a different type to what we get. Interestingly enough, the abstract property thing isn't enough of an annotation for the compiler to be able to figure out what's going on. Kadex, welcome back. Thank you very much for coming back. Yeah, things have changed since you've been here a little bit. Anyway, so we're going to put a at property marker on this. What's this called? I don't know. A property annotation. And that will take out our errors because we can now call these as proper properties, even though they're called abstract properties. Let's see. What was the other one? Also, to do with type checking in classes. So a lot of the time, you're going to have circular references when you start doing type hinting. So we have a CPU that calls out to instructions and passes itself in. And if we want to annotate this as a CPU, that's actually really hard because you get circular references, and in Python it really doesn't like that. So the correct way to do that, which they've added now in Python 3.5, I watched the second episode on YouTube, and there's a code style thing I wanted to bring up. Go for it. Love to hear it. So the correct way to do it, which is actually identified in the PEP, but I never actually read it properly, is just to do a module level import. So instead of from CPU import CPU, just say import CPU, and then down here say CPU.cpu. Now this will work most of the time. However, if this was a line of code that was here, since it wouldn't get executed when it's reading in the file, this would be fine. But since it's actually part of the method definition, you need to put it in quotation marks. And so what this quotation marks means is that it will not get executed. Well, the Python compiler will just ignore it. The type hinter can still see what it is though. So it just means you don't actually have any circular imports. Cool. All right, let's keep going then. So yeah, those were just the first two kind of code style things. Although it looks like Kadex may tell me something else that I should be changing, which I probably should be. So I'm just going to go through and do some more of this annotation stuff. So kind of what I was saying at the end of last episode was I would like to do an instruction, so have an instruction class, but also have an addressing class. So let's take a look at the NES architecture, the CPU architecture specifically, and let's see what we can do. The CPU has a lot of member variables for each register, correct? You may find it cleaner to make a single register variable and make register a dictionary where PC maps to the register's value. That is almost certainly true. Probably what will happen is that, well, I'll take all those registers and push them into... Let me just take a look at this, what I've got here. Yeah, that's very true. So I have a status register, which is actually set to a class. Interesting. What do you think the advantage of doing that is to make a single register? So you could say register.pc as opposed to cpu.pcreg. I suppose you reduce the amount of the amount of variables that you're containing in your class. I guess it's going to depend on how instructions access them. That's a great point, though. I think I will do that, but I will not do that now. I will just put it on. I might just write that down. And then come back to it. Cool. All right. So yeah, let's take a look at some of the different addressing modes that we can do, and then using that, let's start implementing some of them. So the most obvious one that I want to do is a store A, for instance. So you can see there are 7 indexing modes, which is pretty crazy. And we want to figure out what these are, and we want to implement all of them. So they will all pull out a different amount of data, and I want to do it through using mixins, because mixins seem cool. So let's go to the NES dev wiki. And let's take a look if that has anything to say. As always, this is going to be a really good guide for what we can and what we cannot do. CPU. CPU addressing modes. Perfect. This looks like an article that we want. So index mode, use the X or Y register. There are 6 main indexed addressing modes. 0 page indexed, so on and so forth. So one that we've kind of seen here is that we've seen an immediate addressing, which is one that we want to implement. So let's start with immediate indexing and see where it goes. Cool. I'm going to put this into a different file just so that we can kind of separate this so this file doesn't get too big. The instruction file. Cannot create file. Alright, I created this file last time, but it is empty. I forgot about that. Perfect. Alright, so what are we doing? We are creating an addressing type object. Yeah, so we're going to have a base addressing type, which is probably not going to be implementable. I'm just going to make it an object for now. And then, come back and I might make it abstract later. Sorry, let me just... Okay, so let's say we have a immediate addressing. So interestingly, immediate addressing isn't actually a type of addressing. So typically what addressing is meant to do is to look up a location in memory to either use to read or write to. In this case, immediate actually just uses the thing that's in the data, the 8-bit operand, as the value for the operation, rather than fetching a value from memory. But to an instruction, it's actually just another way of addressing. Really what we want the addressing to do is to go and either grab or set a memory location. So when you pass in an immediate, it will just grab the value that's already there. So it's actually an addressing mode, kind of. We're going to pretend that it is. So we're going to say it's an addressing. Now I'm going to call this a mixin. Now potentially we may not have this base object because you're meant to keep the tree on mixins, the inheritance chain, as slim as possible. Pass. Alright, so what does immediate mixin do? So what we were saying last time was we didn't really want to get the data bytes into this instruction. We actually wanted to get the correct just information. So probably what we're going to do is pass the data bytes into the addressing and get the addressing to turn that into the correct data. So an absolute, this should actually say immediate, but yeah. So typically what this is going to be is we're going to say 8D is going to identify this as an immediate, and we're going to say it's going to inherit from an immediate addressing mix-in. Now the instruction length actually depends on the immediate addressing mix-in, so we could actually just inherit that from this. So you can say the instruction length, and really what we're saying is actually, so an immediate, oh wait, no, absolute, no, this isn't even, let's look up what store absolute actually does. Yeah, it actually takes from a memory thing. So actually, okay, so an immediate is actually going to be something different. So what is an immediate? So takes a value from the instruction data. Let's give an example. Would be store in A the value 7. And we're going to give that as an example. And if we convert that to binary, that might be something that says 8D, and then the value for 7 is just going to be 07. So we can see that our data length is actually just 1. So we only have one data value that we're going to pull out, and 1 is reserved for the instruction. Cool. So we have a data length of 1, and we want a def execute. We want the addressing mix-in to be able to either get or store the memory at that location. So typically we want the addressing to, in this case, to get some memory. People say I'm a human linter. That's good to have. Another comment. CLD instruction and SDA instruction, inconsistent naming style. That is true. I'm going to change all of these to be lowercase so that they're all consistent. Whoa. Because otherwise, I'm really struggling here. I appear to be right-clicking. Whoa. No? Alright. This is weird. Alright. Let's never talk about that again. Cool, so they're all CLD. I will change these later on as well to hopefully have a better naming format. But for now, they should be fine. Better to have a human linter and a computer linter than just one, so I'm happy with that. So let's say that the addressing mix-in is going to get data. So typically it's either going to look up a memory location or pull it straight out of the bytes or whatever, but it's going to get you the data that you want. So let's say that it gets in data bytes, which is of type bytes. So we'd call it here, and we'd pass it in the correct amount of bytes. And let's see, in this case, we want to ignore the first instruction bytes. We're going to presume that that's not passed in. We're just going to look at the data bytes. And we're going to say there's only one here, and we want to cast it to int and then return it for immediate addressing mode. So we don't need to dereference it to a memory location or anything. We're just going to pass it back. So let's actually do this. Let's pretend that we know what we're doing here. I'm going to put this in here because otherwise, so let's pretend that this STA absolute is actually an STA immediate for now, and let's see if we can get this to work. Yeah, this instruction length is actually going to be our data length plus 1, and this is going to be our self.data length. interesting. So this comes from our mixin. You know what I'm going to do? I'm going to put this as a property on addressing mixin so that we can call it from anywhere, which is return self.data length plus 1. And then we'll just say for this one, data length is 0. And then it'll get overridden in each of these subclasses. And that will give us our instruction length. And so now we don't need to define it here. We just need to define an addressing mixin. And when we come over here, what we should be able to do, and actually some addressing will have no addressing, which is what these other ones say. No addressing mixin. And the data length is going to equal 0 still. So this is going to be for instructions. Watching you to touch the mountains of programming after for work in uni. Keep up the good work. Thank you very much. Hopefully this is a bit more enjoyable than the work you need to do for uni and other programming. But if it's not, then you must be doing some really cool stuff. By the way, in Python 3, you can create bytes from any number, literal, so... So I don't need to be doing this from hex stuff. Nice. That's equivalent to byte stuff from hex. Nice. Why the, what's the, so you can pass in a list. Right, so you can define multiple bytes at a time. That's awesome. I will do that everywhere. Should Python be my first language? Yes, I think it should. That depends on what you want to do, to be honest. Python is a great first language, and I think it's a great all-rounder language, but sometimes you will have a language that's more specifically suited to what you want to do. So, for instance, you know, a lot of people who want to start wanting to create games or something start using Unity, and then Unity you can use your C# or they have a scripting, I think it's Boo, maybe that's changed since when I used it. So very much depends what you want to do. Find out what you want to do, and if it's nothing specific, you just want to get into programming, you should use Python. It's awesome. Yeah, more enjoying and technical. Programming for uni is just a grind, and in Java, puke. Yeah, I also do a bit of Java work, so I hear you. Alright, so a no addressing mixin is instructions are going to have no data passed to, no data passed. And an example is going to be CLD. So there's no data that's passed to a CLD instruction, it just means to flip a register. Okay, cool. So these are actually all going to be addressing mixins. You'd also enjoy JavaScript, it's quite similar. Yeah. The advantage of JavaScript is that you can use it on the web, obviously, and there's a lot of cool frameworks that use it. But I think Python is actually a bit of an easier language to learn. There's a lot of weird stuff going on in JavaScript. JavaScript is a very good beginner language. Fair enough. Alright, I'll take you guys' word for it. Alright, we've got addressing mixins, we've got SEI instructions. Let's go back to our CPU and let's say, alright, we've got our instruction and now we want to get the number of data bytes. This is going to be our get instruction length now instead of our property that we had there before. And the instruction length is going to come from which type of addressing you use. And this no longer needs an instruction length add back property. Cool. And get the data bytes. It can be as basic as you want, so it's close, and it's so closely integrated. Yeah, I agree. If you want to do any web programming, definitely do JavaScript. I also think Python is very good, but they're both good. The important thing is to just start doing something. To be honest, it probably doesn't matter that much which language you start with, as long as you keep it up and keep trying. If there's a job posting for server administrator, a property named Wait, what? Is it a property? That's true. I should just make this a property. Java, getting the best of me. Alright. Main CPU. Right, okay. So, get instruction length. Kill me now. You're right. Instruction length. Alright. Get the data bytes. So, we want to get the data bytes, and we actually want to pass them. So, we want to get the data from the instruction, from the addressing, not from the instruction, then pass it to the instruction. Right, so we're going to say that data is going to be get data. And get data for this is just going to return an empty array. So let's say this returns an int, array of a list of ints. Okay, let's put this as a base method. And then when we overwrite it, yeah, I agree. Yeah. Knowing Python for being a server administrator is useful, just to do scripts or a lot of existing scripts and stuff that people have written running Python, a lot of the tools and stuff. Alright, cool. We want this to return an empty array, and we want this to return a list that just has the 0th data byte. Cool, so now this data list, data list, that's not a great name, is it? Let's comment this out. Get the data to pass to the instruction. Based on the addressing class. So the data list, whatever, data list is going to be instruction.getData. So now this instruction.getData, due to the way that mixin works, is actually going to reference this function, which comes from the addressing mixin, which is pretty cool. And we need to pass it our data bytes. I'm dropping frames. Ooh, no. Sorry if I'm dropping frames. I don't know if that's it appears that my stream is dropping some frames. Hi, Gamestar707. Can you guys let me know in chat if if the stream is kind of dropping in and out, and I might just chuck down the bit rate on it if it keeps having trouble. Obviously, I missed your work in this emulator. Where does one start attempting to write an emulator? Great point. So if you start at the start of this video, all of the videos on this are on the YouTube channel, which is linked at the bottom. I try to give a bit of an intro to what emulators are and how they work. Stream is okay. Okay, it's just on mine then. So I would say look at that, and then also learning how CPUs work, in particular how assembly language works, is a great way to start. Alright, so get the data to pass to the instructions. We've got our data list. And now what we actually want to do is to do something really dodgy here. Because we want to pass that data to the instruction class. And a second, I think my problem here is this. Are you wearing a jacket? Yeah, it's winter here actually, so I'm reasonably cold. Instruction.getData, data bytes. Cool. So this is going to pass us back a list. and we actually just want to pass it into the execute instruction and hope that it has the correct amount of parameters, and we're just going to do that. So that operator in Python is going to split that list up into its individual components. You're in Adelaide, I'm in Melbourne, but it's still kind of cold. Ish. Cool, so instead of getting in the data bytes now, based on our addressing, we will get in what we want. So now we're going to get in a value for an immediate. We'll get in a value. For this, we will get in nothing. For this, we will get in nothing. Oh, here's my immediate. Oops. And for this, we will get in a value. So now, we actually know that this instruction is going to get passed in the value that comes from the immediate addressing mix-in, which is super cool. So we don't need to worry about doing any byte shifting in the instructions or byte pulling out. That happens all in our addressing module. Cool. Execute. This is now going to get in an arbitrary amount of arguments. That does not work. CPU is CPU. Args. Keyword args. Nice. Execute does not match the signature as the base. Totally does. Why you gotta be like that? If someone in chat can tell why these don't match up, I would love to know. Am I getting the syntax wrong here? Oh well, we'll find out. Alright, so we're passed in a value. For these things, we don't actually need to have any data bytes passed in, they don't happen. And for this one, the immediate mix-in, we're going to need to do its own, we're going to need to do an absolute addressing mix-in. Cool, so let's do that. Let's get all these working. Looks up an absolute memory address, absolute, and returns the value. So an example is going to be store absolute. So it's going to be look in binary location 1, 2, 3, 4. We're going to say it's going to be an 8D, you know, whatever it's going to be. Now this is actually going to be little endian, so we need to remember that. So it's actually going to be 3, 4, 1, 2. Still, oh yeah, completely forgot about that. Let's do that now. So we can change, instead of using from hex, we can just do that. That is way nicer. And then obviously if we wanted to put in multiple things in that list, we could make it a list of multiple bytes, but we actually don't want to do that, so. And here. I'm still wrapping my head around how this byte implementation works in Python. So I'm sure that we'll run up against this wall again. I think that's all of them. I might use one in the CPU somewhere. I don't know. Yeah, I think that's all of them. There we go, Cadex fixed. I'm free from my obligations. So the memory address is going to have to be pulled by this absolute addressing mix-in, and the data is actually going to be 2. So we're going to pull from the data bytes, we're going to get the memory address that we want to look up, and we want to return so this is interesting. Store A absolute. What is store A absolute actually going to do? is store in accumulator. So is that going to write to or read from our accumulator? I don't actually know. I can never remember what the difference is. Let's look up our instructions and we can try and CPU opcodes. Ah, that's terrible. Let's look at the NES wiki page. It's actually pretty good. I actually probably want the 6502, which is the CPU that we're using. Alright. So you can store in A, or you can load from A, or load to A. Actually, we can just look at how I've implemented it. Take value from A-reg and put it in memory, right? So in this case, we don't actually want the addressing mix-in to get us data. We just want it to resolve to an address. So potentially what I've done here is wrong. Potentially we don't want it to return the data. Sometimes we want it to return just an address, and then we'll have something else which will come in and pull out the data if we want to get that data, and something else that will come in and write it. So potentially we might have like a read or a write mix in. So in this case, I'm just going to say the memory address, I'm just going to return this memory address. And I'm going to refactor this get data thing. And I'm going to call it, yes, I'm going to call it get address. Potentially, this is going to end badly, but let's just do it. So you get in some data bytes and you're going to pull an address out of it. And then either that address is going to be useful or not useful. Okay. Now, no addressing mix-in is not going to return an address. An immediate addressing mix-in should probably return an address. I think what I'm going to do is an addressing is going to have two things. One is which is going to be a get address, and the second which is going to be a get data. And you're only going to use the get data when it's one that gets data. Now let's separate this up. So let's have addressing, which pulls the memory address out and keep it to one responsibility. And then let's add in another one, which is going to be, instead of addressing, it's going to be a data, okay, memory reader versus a memory writer. So let's add a Python file, which is going to be memory access. Let's put them in here. So we're going to have a memory reader mix-in. Reads a value from memory. Depending whether it... Nah, let's not do that. Let's just do that in the instruction. Let's just say that an addressing thing is just going to give you your address. We'll have to think about how to do immediates, but for now, let's just say that it returns your address, and the address is not going to be a list of ints. It's just going to be an int, which can be none. So I believe that the thing for that is an option. Oh, no. Optional. So what we're saying there is that it can be none. I really wish that refactor support went through for this, for these type hints. Maybe that's something that'll come through in the future. So this is going to return some ints. Nice. This is going to return none. This is going to return none. Because there's no address here that we're accessing. It's just a value. Yep, okay. Well, let's start with that. And let's just use that and then see what happens. So get the memory location. And this should be get address. Memory address. And then we'll actually just pass the memory address through. So now everything gets a memory address. And some of them don't need it. For some of them it will be none. But they don't actually care. And then we'll use that instead. Cool, so they all get through a memory address, which is actually an int. Right, okay. So here, the CPU status interrupt is fine. Decimal bit, that's fine. I'm just going to rearrange this so that these are in a more logical order. Yeah. So now we want to load the value into the accumulator register. We don't need the memory address now gets passed into us. So what do these different things do? So this one takes an areg, takes a value from an areg and puts it in memory. Memory address int. Yeah. Optional int. That's a great point. So these all can be none. But that won't be if you have the correct indexing mode. So, you know, we're just going to presume that it's type safe. Because, you know, it's Python and whatever. Alright. So here, we got an areg. We get the memory owner and then we set it based on that. So potentially this is just something that could be genericized, where we kind of say instead of an execute function, we'll have a generic execute function. And we just have something where it says, what's the value you want to get? Where do you want to store it? And something will go through and pick out the memory owner and set it for you, and potentially what side effects do you want to have? And we can classify instructions into those kind of things. Does that make sense? I think so. Oh well, let's give it a shot. No addressing mix-in. Immediate addressing mix-in. So we kind of want the immediate addressing mix-in to also get our data. I really do. So some of these will get data. For starting programming emulators, do you think NES is a hard emulator? I do not know. This is my first emulator. But I picked the NES because it seemed like it should be easier than newer ones, obviously. It's kind of like, but it's a very, you know, well-known console and everything, so it'll be cool to be able to get it running and get some known games running on it. Alright, so the no addressing mix-in is just going to return none. This is going to return... No, this is going to return a list of ints, like I did before. I'm going to return an empty list. I'm going to make this return none by default. And so now we don't need to implement that. We don't need to implement this, but we do need to implement get data. and we're going to return. Right, this is all going to take in our data bytes. NES looks a little easier than SNES and a lot easier than 64. Yeah, well, that's the hope. I had Game Boy. Yeah, definitely Chip 8 is meant to be easier. I read a bit about that, and I think probably Game Boy too. But I kind of like the idea of doing the NES and, you know, being a bit optimistic, if you will, as to my chances of getting something done. Yeah, the 652 and the thing are similar anyway. Yeah. I guess the thing is that the newer you get, there's a lot more stuff that isn't standard, and you have to do boot ROMs and all that kind of crap, and, you know, whatever. Keep it simple, I think, with the NES. For now, at least. Maybe when I finish this, I'll move on to another one. Right, so this is just going to return data bytes 0 in a list, and the absolute addressing mode, def get data, data bytes, is going to return nothing, actually. There's for absolute addressing. Right, so depending on if you're doing a read or a write, you want to get data or set data. So maybe I want a set data function, which takes in a value, which is an int. We're just going to return none, and our default thing is going to pass. And then this, get data, is going to return the data that's at your memory location. But for now, we've only got a write absolute, so let's say that it's going to set. So set data is going to do this, memory address, right, so maybe get data should just have the address passed to it, and this should be an internal function. Alright. I bet you will. Yeah, we'll see. So I'm just going to keep trying to hammer out what the structure of this mix-in is going to be and where the responsibility comes. This will kind of work itself out pretty quickly. And what I think I'm kind of trying to say is that actually, by default, this get data function should actually probably just be these two lines. No, this line, get data. Right, so we'll need to get past the CPU. Interesting. So, okay, so who's the responsibility of this going to fall to? What do we want the instruction to do? We want the instruction to specify where it's taking it from and where it's putting it. But where it's taking it from and where it's putting it is either going to, one is going to depend on the addressing and one's going to depend on the instruction. So I think if I'm going to do a write, so an STA is a write instruction. You're a skater. Yes, I am. The thing in the corner of my room is a skateboard, actually. You can kind of see it back there. It's not a great board, but it was pretty cheap, so I don't skate much anymore. I basically just use it to get around, to be honest, when I'm going more locally. So we're going to have an immediate addressing mix-in, and it's actually going to read or it's going to write. And I think I might make this distinction. So I might make this a write immediate or a read immediate. So you're never going to write immediate. So let's just rule that out. But let's say if this is an immediate read, it's going to read a value from the instruction data. And then we know that since this is the read, this LDA instruction is going to need to implement the write, which we're going to call set data. And the value that we want to get yeah, since it's a thing, we actually just want to say cpu.areg equals value. Right. So this is all it is that it should get passed in a value, which should be passed in from, so up here, if I have my execute function, my execute will just take in a CPU, and will take in the data bytes, and what it's actually going to do is get the address, get the set, and then do any side effects. Okay, so memory address equals self.getAddress. Now, this is not going to exist yet, but we're going to mix it in through this addressing mixin, so it will exist. Cool. Memory address. Then we want to get the data that's at that thing, and we want to pass the data. So I want to get the data. We've got to pass in the data bytes. And if it's a read absolute, then we're going to need to pass in the address as well. So let's pass in both, and then it can decide which to use. So we're going to pass in a memory address and some data bytes into our self.getData function, and then we're going to call self.setData, which probably should be called write. We can change that later, which is either going to be implemented by the addressing mixin or by the instruction itself, and that just needs to get passed in the value. I'm going to call this value instead of data, and it should also probably be passed in the memory address, even though it might not use it. Cool. So now we don't implement the execute anymore. And then I'm actually going to call a self.sideEffects function. And that's just going to be for things that don't need any of the above stuff. So let's say we have a side effects function up here. It's going to pass. Alright, so normally we have no side effects. I actually snowboard mainly, KDX, instead of skateboarding. But my snowboard is under my bed, so not visible, unfortunately. Alright. This is getting nice and confusing, but let's keep going. So a no addressing mixin is not going to get an address, it's not going to get data, and it's not going to set data. Cool. So all these instructions, SEI instructions, need to do is just call side effects, which I suppose should be passed to CPU. So probably set and get and everything should also be passed to CPU. So side effects is going to be CPU.CPU. This is also just going to be a side effects function. love snowboarding. Snowboarding is super fun. I would highly recommend it if you can get into it. It takes a while to learn and actually enjoy, but once you've spent a couple of days doing it and kind of falling over and bruising yourself, it's actually super awesome fun. Right, okay, so these ones are going to work. So this is a status instruction and this is a status instruction. So they just need to override side effects. Now, a load A is going to be, load A immediate is going to be a write function. I'm actually going to call this write, just because it's going to save me trouble in the long run. Right. My right click does not appear to be working at the moment, so I'm just going to manually, paste this everywhere. Right, so we can get rid of this function now. So basically a load immediate is just going to have an immediate read addressing mix-in, which is going to so it's going to come in here. When this instruction executes, it's going to get a memory address. It's going to return none. It's going to pass get data to CPU memory address data bytes. Get data. And that's just going to return the 0th data byte. Write is going to call this, which is going to right. Okay, let's get some of these functions in here. And def get data for the same thing, except this is going to be data bytes. It's going to return a list of int. So we kind of want to have a matching signature here. It might be a little useful for your bootload sequence. Alright, copy link address. It's JavaScript, that's fine, I can read that. Currently reads and checks a NES ROM header. Yeah, okay, so this is what we were kind of starting to look at. Yep, so the ROM size, for those that haven't seen this kind of stuff before, so basically if you're looking at the Super NES ROM, the first 16 bytes are the header, and then the program code kind of starts here. And this will tell us information about the ROM. So it spells out NES, so the first 3 characters, but then things like this will tell you how much program code there is, and then how much data code there is, and so on and so forth. So we kind of have we kind of just cheated that implementation when I did it here and hard-coded some values based off the Super Mario Brothers ROM, which we're using. But this appears to be actually reading it in. Yeah, so finding the PRG ROM size, which is in 16 kilobyte increments, the CHR ROM size, so on and so forth, bit 4, bit 5, bit 5. Yeah, perfect. So I will come back and implement this when is padding okay. No, we just assume that everything is right. That's the Python way. I will come back and implement this. How do you bookmark in Safari? Is that it? Yeah, I think that works. This will be implemented. I'm not going to do it right now, but I will come back in a future episode, and when we're properly doing the boot sequence for the ROMs. Oh, thank you, KDEX. That is, well, I don't know if have done that as a result of watching the stream, but if you have, I'm glad you're getting into it. Hope you enjoyed writing. Let's see. Alright, let's just do that, just to, make our lives harder in the future. Because I keep having colliding variables. Alright. So let's keep going. So, get address. Yeah, let's just do def. Get address, which is going to return a int. Optional int. And we're just going to have it return none. Cool. So we're kind of going to do some funky stuff here where we define what all the functions are going to be here that we can call. And then we're actually just going to overwrite them in the mix-ins. So this is going to, because they're mix-ins, they should be resolved before these base instructions come in. So we're just going to overwrite the bits of functionality that we want when we want them. Which is kind of pretty dodgy, but I like it. Alright. This is... yeah, so these all need to match up. And side effects probably won't be defined by the addressing mix-in, so we probably don't have to worry about that. Get address needs to take in some data bytes. Immediate read addressing mix-in. Cool. Okay, we're getting there. All right. So store absolute is going to get a value to store, and then it's going to store it in memory. So it's going to take from an A register and put in here. So technically, what we want to do is, since it's store A, we just want to overwrite the get address function. Is going to return us our memory address, but we don't actually want the data to come from that memory address. We want the get data to be CPU.A, whatever values in CPU.areg. And we actually want we want no side effects, no additional side effects, and then we just want to overwrite the write function. And we want to say, we already have got the memory address. So we want to get the memory owner and we want to write to it. And we want to write the value. Nice. So this is pretty cool, I think. Maybe. Side effects sounds like a property, but it's actually a method. How about apply side effects? Yeah, definitely. My right click is still broken. So I'm going to have to, there we go, control. Alright, so we're going to rename this to apply side effects. You are completely correct. Is it effects or affects? There's an important distinction. I can never remember. Let's get it right. Affect is a verb. Okay, fine, whatever. If I do side effects. Cool. Yeah, sweet. So these CLD instructions are just going to be side effects. SER is going to be a side effect. STA is just going to get the areg and it's going to write it to that location. Now, ideally, this should probably go in here, but only if the memory address is not none. Can a memory address be none? Yeah. So if memory address is not none, we want to do something. We want to say, get the memory owner of that memory address and set the but do we always want to write? No, we almost certainly do not. Okay, no, never mind that. Every function's just going to have to implement that for now. Affect can only be used as a verb. Yeah. Alright. This code definitely needs cleaning up for various various reasons, but let's get it working, and then let's see what happens. Cool. So an absolute, well, at the moment we're doing absolute. Store sta absolute is a write function. Absolute addressing. So we want it to get the address. Do we need it to get the data? No, the data will be gotten over here. And the write we don't actually want it to do. We just want it to get an address. Yeah, so immediate's going to be a special case where instead of overriding the instruction, it's actually going to override get data because it doesn't need to look at the memory address. It's just going to return straight from the data, whereas everything else will just get an address. Okay. What are the odds that this works? So now we don't need this anymore. We're just going to execute with ourselves and pass in the data bytes. Alright. Let's give that a run and let's see what actually happens. I have no idea. Failed to run. It didn't fail to run, it just, I don't know what happened. Process finished. Do I enter the loop? No. Do I start my main function? Am I running the right code? Ah, I'm trying to run instruction. I don't quite know why that was. Alright. Cool. So we get our first instruction. And our first instruction, I'm going to move this over here so hopefully it appears from behind my webcam. What is the instruction going to be? It's an SEI instruction. So the effects that this instruction should have should just be to apply the side effects. So let's actually step through this line by line. So let's step into the function and then go through the thing. So the memory address, it shouldn't care, so it should just get none, which it does. The value, it shouldn't care because it's the side effect, it should get none. And empty list, yep. The write function should not do anything, so that's fine. Actually, I might just do this again, but I might make this write function generic, but only write if there's a write flag. And I'll set the should write or will write, writable, writes, yeah, sure, which is going to return a boolean, which is going to return false by default. And then down here, instead of having to implement this write function, we can just say writes, let's call it writes to memory equals true. And then it will just do that writing stuff. Whereas up here, we're actually going to override the writes function because we want to write a register. Actually, we might be able to make our generic write function do that, but for now, let's just do that. Cool, so now it has to opt into that functionality. All right, let's rerun that. So we're going through an execute for an SEI instruction. So memory address should be none. Value should be an empty list. Self.write, as well as, so self.writes to memory should be false. This write function won't do anything. And then apply side effects should, if I step into it, should set the interrupt bit. Nice. All right, let's run to the next breakpoint. So now we have a new instruction, which is the CLD. So that should do the same thing. Memory address should be none, so on and so forth. Yep. Let's step in. Right, so this is where it's going to get interesting. So we're now executing an LDA immediate instruction. So an LDA immediate instruction is going to load to the A register. So it's going to get a, not going to have a memory address because it's immediate. Yep. It's going to have a value which is going to come from the next value in the data bytes, which should be 16. And if we look at our thing over here, 8D, A910. So this 10 is the immediate value, and 10 in hexadecimal is 16 in binary. In decimal, which is what we see here. Now, if our self.writes to memory flag is true, is false, so this writes is going to be overwritten. So let's step in and see what happens. Yeah, so we've overwritten the write functionality, and so the A register is now set to the value, and then there should be no side effects. I wonder if I can make this getMemoryOwner function return the CPU itself, so that we can write registers. And so who was mentioning that before? I presume it was Cadex. Yeah, it was Cadex. Cadex was saying this before, and he was right, it's probably going to be better to implement the CPU as a memory owner because it does own memory, and have the RAM be accessible through that. And then the write function will get the memory owner and will call set for the memory address, and then the CPU internally will just know how to map that. The only thing we need to define is what's the address of the A register. Which at the moment, we don't have a memory address. Actually, I'm going to leave it like this for now, where we just say the write function is going to say, if you're going to set a register, just overwrite the write function instead, and leave the writes to memory function for when you're actually writing to RAM or something like that. Cool. Let's go through, we've now got the last one, which is the SDA absolute, which means take the value from the A register and store it somewhere in memory. So the value in the A register should be 16 because we just stored it there. So we're going to get a memory address. So let's actually look at what this instruction is going to be. It's AD0020. So this 8D maps to store absolute. The next 2 bytes are going to be our data bytes, which are 0020. And since it's stored in little endian, 0020, so store A AD0020 actually corresponds to store an A 2000 because you flip the bytes. It might be a good idea to get into running some instruction unit tests so you don't accidentally break some other instruction if you proceed implementing more of them. Yep, that is a good idea. I'll do that. I'll do that. Well, once I've finished stepping through this and kind of doing some manual verification, let's write some tests and see if they're actually doing what we think they're doing. What's up, son? Not much. Welcome, Extafile. Yeah, let's keep going then. So, memory address should return where we're going to put this, which is going to be 2000, which is a hex value, which is going to be 8192, I believe. Should be our memory address. Let's see if that's correct. Memory address is none. Fair enough. So either I've done something wrong or I'm going crazy. So store A. Where is it going? Yeah, so store A should get an address from immediate. This is not meant to be an immediate read. This is meant to be an absolute. Yep. Yeah, this is where tests would be handy. So let's rerun that and let's say that the store A is in fact doing what we think it's going to do. And then we'll write a test to confirm that we don't break this functionality. Alright, memory address should be something that's not none. 8192, correct. The value that we want to write should be whatever's in the A register. Yeah, which is going to be our list of 16. So get data is going to return a list of integers. We'll probably need to remember that. Can get data ever return more than one value? Maybe it can only return one value. Yeah, okay. This should actually be an optional int, not the other way around. I think. One of those things. So this doesn't need to return a list anymore. This is going to return data bytes 0. Get data, and then any get data is down here, cpu.areg. Cool. So let's go through again and let's check that this is actually doing what we expect. Memory address should be A192. The value should be 16. We're going to call the write function. Right. So these addressing mix-in things should just call super. Oh, interesting. This may break my function. Right, so that's not going to work. Alright, so we don't actually want the addressing mix-in to define these functions. We just want to overwrite them. Otherwise, we're not going to get the... If you expect it to return 0 to infinite values, you might make getData a generator function. I'm not sure if I do, though. I don't know if it can return multiple. Maybe I'm wrong about that. I might have to come back and change that, but my kind of thought at the moment is that we should only really be working on one data value at a time. I think each instruction should only move 1 byte. If that turns out to be wrong, then we'll come back and fix it. All right, let's go again. Store A. All right, let's step through. So memory address 8192, value to 16. Write is, do we write to memory? Yes. Cool. Apply side effect should be none. Now I've kind of done some basic stepping through, but as Kadek said, let's write some tests because the hell is mine? So that we can actually verify that we're doing what we think we're doing, because the likelihood is we're probably not. Test instructions. Cool. I'm probably going to use PyTest here, because that's what I'm used to using. So let's work on our thing, and then pip install PyTest. For those of you who haven't used PyTest before, it's kind of just the, well, at least when I was using it, was the de facto for how you do this kind of stuff. You can just create test classes, I'm pretty sure. I'm going to look up how to use PyTest. I can't remember. Cool. Examples. Asserting. And we want that one, I believe. Okay. So we can do fixtures. At the moment, we're just going to do some function-based stuff. Okay. Test LDA immediate. So if we run tests on this folder, let's just create a Python tests, py.test. The target should be NES. No PyTest found. Yeah, okay, I installed it in the wrong virtual environment. It might be cool to have an at-writes to memory decorator. That is true. So you'd put that on the instruction instead of having a property. Yeah. It's a good point. I'd have to go back and read up on how to write a decorator again. But alright, how about I put that on the list and then I'll come back to that after I do some tests. Because then we can test that the functionality is working, and then we can test that we don't break it by making it a decorator. which is good. Right, okay. So LDA instruction is an LDA instruction. We actually want to kind of just test the execute thing. CPU equals CPU. Whatever. What else do we need? Some data bytes. So these are the bytes are going to be... So let's actually pull out our LDA instruction, which is 8910 bytes 0x A9. Right, so this is what an actual LDA instruction is going to look like. Instruction bytes. CPU. Alright, we're just going to mock some stuff up. Pip install mock, pymock? Okay. So that could be magic mock stuff. So those are pretty cool. Mock. Nice. So what magic mock stuff allows you to do is just pass in things that just pretend to exist. We don't actually really care if they exist. CPU and our RAM equals our magic mock. Now we can put all of this into like a fixture and then reuse it, which we'll do in a second. So let's say that the CPU gets a... Does it need RAM PPU or... What? RAM PPU. Expected type RAM got magic mock instead. Well, that's fine. You're going to have to deal with that. An LDA instruction is an LDA instruction. So let's say that we're running our tests. All test passed. Cool. Because we don't do anything. So after we call LDA instruction, what do we want LDA to have done? We want the A register to be updated, and it's LDA immediate. So we want the thing to be updated with the value that's in this byte. So we kind of want to say assert that we want to insert that the identifier byte is in fact bytes 0, so that it gets matched up correctly. Bytes 0. Instruction bytes 0. So this will actually return not a bytes thing. If I have to do 0 to 1 to get that back. And then we want to say, we want to check that value has been loaded into areg. So I want to assert that CPU dot areg.value is 0, and then after we run the execute, so ldam.execute CPU instruction bytes 1 to the end, then we want to assert that the areg is equal to bytes, instruction bytes, we want the second instruction byte, and we want that turned into an int. Ha! Man, we're getting there. Alright, does that work? No. Sick. CPU.areg equals 0. CPU.areg, I need to call CPU.startup. I probably should just do that in the CPU constructor or whatever. Boom! So we... That's pretty cool, eh? Let's get some fixtures going. Fixtures. Not found. Let's get some fixtures going, and then we can start writing some better tests. My internet appears to be quite slow. Ah, was I on the wrong page there? Okay. Yeah, here we go. Yeah, this is what I want. So I want this, and then I want to be able to pass it in as a function argument. Setup. It's a fixture, and we want it to do all this crap. Set up PPU. Let's do another one that sets up the RAM. And then we'll have one last one that's going to set up our CPU. Probably should just return these. So if we ever want to return an actual PPU or something, set up CPU. This is going to take in a PPU, RAM, PPU, return CPU. So you can now pass these in as function parameters. So you've defined them as fixtures. They get executed, can be passed in as function parameters. Then here all we really care about is getting passed in the CPU, which is this thing. And now we don't need to do that, we don't need to do that. Cool, so an LDA instruction. We define our bytes, create the instruction, test that it works, and, you know, assert a before and after state on our expected values. A lot of this stuff could be automated, but I actually don't mind doing it like this, where it's a bit more verbose. So we just got to check that the identifier byte is the instruction byte. So we can probably, yeah, look. So instruction bytes. We'll have a function to do this, instruction and instruction bytes. And we'll just say this. So that will just assert that the instructions identifier byte is correct. Cool, so we now are testing that the instruction byte is correct, and then we want to check that the value's been loaded into a reg, so we check that it's 0, we execute the instruction. I can just make this get data bytes, just so we're, we don't make an error in indexing. So return everything but the first byte. And then we want to say the areg has got to equal whatever's here casted. I can just say equals get data bytes. Whatever the 0th value in the data byte says. So that should still work. So we just have some kind of basic test methods now that will help us test. And so this is all the code that we need to test an instruction. Cool. Let's keep going then. We just tested our LDA and it did what we wanted. Maybe. Test store absolute. Store absolute equals S. So we've got the instruction. We want to check the instruction bytes. And then we want to do something different. So we typically want to check a before and an after state. Alright, what are the instruction bytes of a store absolute actually going to be? So let's come back to Wikipedia, and our store absolute is 8D. So if we look at the thing here, it's 8D0020. So I'm actually going to use the instruction that's in here, just because I know it's a real instruction. I'll just do this and then so again, I'm just converting this into hex and giving it to Python. Alright, so what does the store a absolute do? So we want it to check that value in areg has been loaded into memory. So I'm actually going to copy this. So let's say we assert that the areg starts at 0, and then we want to say cpu.areg is going to be equal to, 8 or something. So we're going to set it, and then we want to check that this value gets passed through, this 8. Yeah. Value to store. Right, so let's do it then. So we have a value that we want to store that's stored in the A register, and we want to execute the instruction, so none of that changes, and then we just say we want to assert that the memory location at whatever this thing says, which is going to be 8, I know is 8192, is going to equal value to store. So now it's not going to be the areg. We want to test that the value at memory, the value at the memory location, is value to store. So now what memory location do we want? So it's a store a absolute. So it's whatever value comes out of this absolute thing. So let's figure out the memory location. And I know that is going to be 000020. And then flips because that's little endian. So I know it's going to be going to turn into the hex value 2000 when I read it out with little endian mode, which corresponds to 8192 in binary. So the memory location is 8192, and the value at the memory location is going to equal CPU dot get the memory owner of the memory location, which is actually going to be the PPU, but you know, we just have a get memory function. A memory owner mix-in which should have a get and a position. So we've got the owner, and then we just want to get the value at memory location, and that should give us our value. Cool, so we queried the CPU and said who owns this memory, and give us the memory at that location, and that should equal the value that we originally wanted to store, which is 8. That didn't work. Perfect. This is what tests are for. Alright, instruction.execute. Right, so since we're storing things in self.rom. Right, so we're actually going to need to make ROMs. We're actually, whoa. CPU.rom. Startup. Run ROM. Right, so the ROM okay, so this get memory owner function. Interesting. What if I make the ROM a mock? What's going to happen there? Unalterable types. Yeah, so I'm going to need to give it cpu.rom.memory start location .return value equals 0. So I'm just mocking up things here so that when Python calls them in this code, it can just know what they're meant to be. I believe it's just meant to be for I don't know, 0x to 1FFF. Alright. Okay. Cool, so we're now mocking up our ROM, so self.rom.memory start location. Yeah, okay. So maybe that should do something different. Cool, so now can't order memory owners because we pass them in as mocks. Let's actually just make them real for now. So RAM equals RAM. PPU equals PPU. See if that works. Alright, so what's our value at the memory location? 8, and what's our value to store is 8. Right, so all our tests pass. Cool. We're testing things, I suppose. Let's test our last instructions that we've implemented. And then let's create more. So let's test SEI. So I believe SEI is 7, 8. Okay. Is the bytes associated with that. and we want it to be an SEI instruction. Sorry about that. And then we want to check that interrupt bit has been enabled. So when the CPU starts off, the interrupt bit is part of the status reg. So, or gets enabled. So it's part of the status reg. So we want to check that the status reg dot interrupt bit equals true when we start off. And then we want to execute the instruction, and then we want to test that it now equals false. No, okay. Is true, is false. Nice. The CLD is going to be very similar. So CLD instruction is D8. And check that. What does the CLD instruction do? I don't know. I can't remember. Clear decimal. So let's just check we have that SEI the right way around. SEI. I swear there was something that... taught us how to do this. Okay. Return to main page. So let's just take a look at some of this documentation, because we probably don't want to get this wrong in our test code. Alright, let's look up 652 SEI. Maybe it was in here. Opcode matrix. Yeah, it must have been this page. I want to remember this page. Nice. Set interrupt disable status. It's going to push 1 to I. So it's actually going to set it to true. Okay. So it's going to start off true, I think, if I look at my power up state. Because our status is FD. Alright. 0x FD. Holy shit. To binary. Oh, it's a P is 3, 4. Okay. 1101. So 001, 011. 001. So the interrupt bit actually becomes before the decimal bit. True. 11. Yeah, okay. So the interrupt bit starts true and actually gets set to true. So let's set it to false and then set that it turns true. Actually, I'm modifying the wrong instruction. Cool. And the CLD, check that the decimal gets disabled. So the decimal bit should start as true and then it should end as false. Okay, now this is not going to work, presumably. All tests passed. Huh, okay, I must have... Oh, yeah, I implemented SEI correctly. I was just testing it wrong. Okay, that's good. That is good. We've got tests now. So really what we want to be doing is, as well as having one for each one of these, we could probably just test these mix-ins and stuff, but for now I'm just going to have one per test, so that when we do something like, hey, let's check whether we can make this a make this a decorator, then we can see whether we've broken any functionality. So let's look at Python 3 decorators. Python 3 patterns idioms test.readthedocs.io. That's a web URL. Yeah. How do I define a decorator? Is there a... Holy crap. Just want a simple example. Okay, cool. This is what we want. So we actually want a decorator, which is a writes to memory decorator. Takes a function, returns the function. A decorator should really just be a function. Yeah, but I think you need to wrap it, right? Like this. Maybe. What do we want this decorator to do? We really want it to be a class decorator, don't we? So it's actually going to take in a class, and then it should probably set... Well, let's look up class decorators. That's not good practice. Oh, there you go. Python 3 class decorators. Everything in Python. Cool. Meta classes, no. Decor. Okay, so we can just call it on the class, and we can do this. Writes to memory, and the class dot something should equal true. What a terrible way of doing it. This is probably a horrible way of doing it, but I'm going to do this to start off. So if we have a writes to memory decorator that will just set our property to be true, which we can just set as a class method. And a property. Can we do it? What if I just do writes to memory equals false. What's the first underscore? Just making it a private function, or a private variable. That's just, it doesn't do anything in Python, as in there's no, you can still call these things, but it's this convention to put the underscore to make it private. I think also it won't come up in autocomplete and stuff like that. But this is kind of the way you do private stuff. Alright, let's run our tests. Test passed. Now, that's probably a terrible way of doing it, because all I'm doing is like, setting a private variable. But I don't mind having this this decorator syntax be a bit, it's a bit more obvious what's going on. So now self dot writes to memory should be true. Yeah, so it's purely just a syntactical thing to integrate private ownership, so that nothing outside should set it. Sorry. All right, perfect. We've got everything that we want, kind of. Maybe. Oh man, my brain is falling apart. Oh well. Upwards and onwards. So what are the different types of addressing that we've got? So we've got 3 types of addressing at the moment. Let's look up the other types of addressing. And let's see if we can implement them. So we've got 0 page, absolute, indirect. So as well as this, sometimes you'll be able to pass in absolute and X, for instance, or absolute and Y, which will tell you that take the whatever is in the absolute and then add whatever is in the X register to that value. I believe that's what that means. I did read about this. So on this skilldrick.github.io, let's look at the addressing modes. Cool. So absolute. So this is one that we've implemented. So you can just pass in 2 bytes or 4 hex characters, and it just takes you to that memory location. 0 page, whatever. Absolute X, absolute Y is what we want to do. So these are the absolute addressing values of the 0 page 0Y. Alright, well, yeah. So load 5 into the register and then store FF. Yeah, so it's just going to add. And we're going to need to implement overflow. Interesting. But I think at its core, what this thing is going to do, absolute addressing mixin, absolute addressing X. I might make that a bit more clear. With X mixin. Looks up an absolute memory address. Including adding the xreg to that address, and then it's going to return the value at that address. So for instance, the store A 1234 is going to turn into memory address is going to equal 3412 plus whatever's in the X register, if that makes sense. I think I'm approaching the point where my brain is getting pretty exhausted, so I might actually give up here. And by give up, I mean pause and come back at a later point. We've kind of, it was a bit slow progress today, which it was always going to be, but I feel like we've got some tests going. We've got the addressing mix-in stuff going. The big stuff now is just going to be implementing all these things, and they should smash out pretty quickly, seeing as how we're going to be able to implement all the addressing modes, and then basically that's a seventh of all the operation. You know, every different operation, like a store A, absolute, like a store A, sorry. Now you just need to implement that once with every addressing mode. Whew. Yeah. I think we've made some good progress on how this is all going to fit together. Particularly with the way instructions are executed, the format in which they're executed, and how these mix-ins are going to fit in. Alright, let's do this. Let's comment this out so I know that it's not done. This is not real yet. And let's get some source tree up in here. Yeah, scrap. Git add all Hi Andy. Hello, Black Stealths. Welcome. Unfortunately, I'm going to be finishing up pretty soon. So, hello and probably soon goodbye. Git status. Cool. Git tag. Let's see what tags we got. So git tag. And I'm just going to do this over here. Git push origin master tags. This will go up on YouTube with the other episodes. So, although it is sad, you can relive this experience in a slightly less real-time environment. Okay, let's just check that pushed. Refresh. Yeah. That worked. Right, cool. So the main thing we kind of got done today was getting addressing mix-ins going. So they're not finished, but we've got the basis of what they can do, and we've tested out that they're, working in theory. We've got an interface for them. And so basically the next thing to do will be to come back, finish those addressing modes, which to be honest, probably won't take very long. And then implement more base type instructions. And then we should be able to smash through writing all the instructions pretty quickly. I think in hours rather than a longer measurement. Yeah, and we got some tests. We got some tests going, which is really cool because these will come in useful when we start breaking things by changing functionality. And potentially these tests should just test the different addressing modes, and then we should probably have both, really. One that tests the addressing mode and one that tests that the instruction does what we expect. They're not too expensive, they just take up space, so I don't really care if we have a huge test file that has a couple of hundred lines in it, as long as we get our expected behavior. Perfect. Alright. Yeah, I think I'm going to head off, unless anyone has any questions. I'll just kind of wrap it up, and yeah, I'll probably stream again tomorrow. I'm a bit tired today, so I'm gonna get some sleep and then come back fresh. Probably round 2 p.m. 2 p.m? 2 p.m? I don't know, actually. What's the time at the moment? So I'm in GMT. 6 a.m. Right, around 2 a.m. I'll probably be streaming at around 2 a.m. GMT time, which I think is around 10 p.m. in America, around midday-ish in Australia. Thanks for coming along, Cadex. I haven't forgotten about the startup ROM code that you have written, so I will come back to that probably pretty soon and put that in, because we'll need that to actually be able to read in ROMs that aren't this one, so unhard-code it. Yeah. Thank you very much for watching, and I will see you all next time, or sometime.